Hi, welcome back. You're in room one. I hope you enjoyed your morning tea break, especially the catering. I wonder how that was. I got a nice cup of Lady Grey tea. I brought home from myself. I brought from home. So as I said, you're currently in room one, and this session is with James Tanton, and it is pencil pushing. Do the interior angles of a triangle have measures summing to 180 degrees? James is coming to us from Arizona, and we'll be commencing right about now. And I would like you to welcome James. Thank you, James.
Thanks, James.
Yes. Okay. Hello, everyone. What an honor to be speaking to my homeland from Phoenix, Arizona. It's currently almost dinner time for me, so I will stave off hunger pangs to get this fabulous experience with you guys today. So thank you so much for having me. A real honor to be speaking to my homeland. I'm not quite sure if you were there with me for the keynote just an hour ago, but I was doing something very strange at the beginning of that talk. And I'm going to start off this talk the same way. Namely, I want to make sure everyone is fully aware that there exists an international salute to mathematics. Are you aware of the international math salute? Now, I can't see you, I can't hear you, so I don't know what you're answering. You're probably nodding your heads. Hopefully you're nodding your heads. I hope everyone on this planet knows, because actually, if you Google International Math Salute, you'll see I'm not making this up. There truly is one, and it's probably people in Belgrade or Tokyo right now doing the math salute. So I'm going to teach you the math salute as part of this idea of making sense of angles, because this involves angles. All right, here goes. So you need your morning tea, your Earl Grey out of your hands. You need your arms completely free for this. Yep. Put coffee cups down, and I'll put down my dinner plates down, all the rest. Goes as follows. Arms out front. It's a very strange salute. Put your right hand over your left hand. That's the hard part, right over left. Okay, got it. Then you go palm to palm. Okay, and then the salute gets weird because you wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, just come on back. What? Looks like I can see one person. Looks like I need to do it again. I'll do it again. I'll do it sideways this time so you can see it from a different angle. All right, arms out front. Okay, arms out front. I think the other person I can see needs to do this as well. I can see two people. So yes, I know. I've just got rolling eyes. Right hand over left hand. Yep, right over left. That's the hard part. Palm to palm. Right, then it gets weird. Wiggle the little fingers. Then you wiggle the thumbs. Then you wiggle the little fingers again. And then when you're ready, just come on back. Whoa, what am I doing? Okay, so if you were at the keynote earlier on, you'll realize I did the salute and I didn't actually give it away. Since you've come to see me, if you're one of those people, twice, I'm going to give away the solution here. But actually, there's a really lovely piece of maths pedagogy here. This is a great maths lesson behind this. I've given you a problem. You've got a problem, which is, I don't know how to do a math salute. But actually, I've given you a very special problem. I've even told you what the final answer is meant to be. It's this, your arms untangled. So you've got a problem and you know what the answer was meant to be. So here's a really good strategy in maths and in life, and mathematicians do this all the time. If you've got a problem and you think you know what the answer should be, either you do know for sure or you've got a good hunch of what it could be, start with the answer and work backwards. It's such a simple idea that most people forget to do it because it's so simple. We get it's incredibly powerful. So let's see if we can do this. Let's start at the answer. Here's the answer. You have to say to yourself, okay, can I reverse engineer this? Can I undo this answer? And you say to yourself, okay, where did this come from? So everyone try it. Have your answer classed? It must have come from your hands turned 180 degrees. Okay. You say to yourself, well, okay, well, where did that come from? So my fingers are curled together. That must have come from my fingers not curled together. Okay. Now I'm going to pause here because I bet that feels very weird. So I'll just take you at the end, and we've got this really strange weird middle position. Weird feeling middle position. So actually, I'll pause now, since I've given you half the hint. Can you now start at the beginning, and so I'll get to that same funny feeling middle position? Something's going on. You know I'm doing something. And that might be helping some people. It's helping some people out. And if you're like me, it won't help you out, because I'm really slow at these things. I am terribly slow at doing maths and puzzles and stuff. That's okay, because and someone else figured it out. Okay, I see at least two people figured it out. So it is possible to figure out. You guys are way cleverer than me. But then, for those that are like me, let me actually give it away. I'll give it completely away because that's the mood I'm in. The idea is that when most people go right over left, palm to palm, most people swing their thumbs in opposite directions, and then you're actually totally stuck. You can't do anything. What I'm actually doing is being sneaky. I'm actually turning my thumbs in parallel to my left, which feels completely unnatural, but then you're ready to come back. Now, that was too fast. I'm not really explaining it. I'm just giving you the principle. I'm twirling my thumbs in my parallel to the left. So here's the idea behind that. I've got several ways to think about it. So I'll give you 2 or 3 ways to do it. So one of these might click. One is, imagine you holding a big red rubber ball. It has to be red. And all I'm really doing is turning the ball upside down. And imagine doing that. And then I'm clasping my hands. And then you realize, oh, I can just come on back. So that's the principle. I'm actually like imagining I'm turning a big red rubber ball over. That's kind of what I'm doing. So the trouble is, I'm doing it with my wrist touching. I'm doing that same motion with my wrist touching. So that's the tricky part of this. So that helps some people, but doesn't help everyone. If you're like me, it doesn't help me then. Let me do it really slow. Let me really break this down. So I'm giving away the math salute. So actually, I don't know how much you're meeting other people at this conference. If you're seeing other people, those at the keynote are going to be very confused. They're still trying to figure it out. You'll now have the answer given away. Right hand over left hand. Great. Each thumb is currently pointing upwards. Each thumb will turn 180 degrees and will go downwards. Your top hand, your right hand, there are no tricks there. Your thumb just goes down. No tricks on that one. All the sneakiness is with your left hand, your bottom hand. Your thumb is currently up. It will turn 180 degrees downwards, except it turns in the direction that feels wrong. Thumb towards the palm. That make your thumb touch your palm. But make your thumb slide down your palms. Just slide down your palm. Really make it slide down your palm. It feels so wrong. It's so wrong. But it's what you need to do to wiggle, 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 and come on back. Whoa, whoa, crazy, crazy. So here's your optional homework for tonight. Now that you've got the knowledge of the International Math Salute, your job is to secretly practice this like 20 times in a row until you do it as smooth as I can myself and spread it all across Victoria. Agreed? Because I just heard on US News even that Victoria is now out of lockdown. So you can spread it all across Victoria. That's a good thing to spread. Go for it. Go for it. Let's make this a truly international math salute because I don't think Australia is quite yet on board with it. So great. All right. So what I'm going to do, I'm going to be talking about pencil pushing and angles. I'm in a little predicament here. I thought I was speaking to a group of teachers for the upper grades. I understand this is years 1 through 6. So this is going to be interesting. So I'll do my best to just talk about angles from a general perspective that's appropriate for you. Please type into chat any questions you have about angles as I go along, because actually I was prepared to focus on upper level work. No worries. We can work with years 1 through 6. And my fabulous co-hosts here are going to read chat and interrupt me with any questions that come up that you might type in. We also, I believe, have a little bit of delay, like a 7-10 second delay between me saying things and the video being processed and churning and being on your screens. So I might be like chatting away and there'll be like 10 seconds later, there might be acknowledgement of you having typed in a question. So are we up for that game for the next 35 minutes or so? The answer has to be yes. We've got no choice. You're here and we're doing it. We're playing that game. So I'm going to share my screen. And hopefully it says pencil pushing, share. There we go, there we go. And I kind of started talking about angles already. I don't know how much a part of they play in the very early curriculum, probably not too much, maybe the concept of it. But as a high school teacher, when I was in, I realized that kids do not really have an intuitive understanding of angles. So it could be very helpful for us today, just for our adult selves, to get an intuitive understanding of angles so that whatever your curriculum does, at whatever level it is, you can see the fuller story and take the appropriate steps as appropriate for your fabulous kiddos at whatever age level they're at. That's the goal today. So I'm speaking to your adult selves, not as teachers per se, but as professionals that know how to take a mathematical piece of understanding that you can see the fuller story for your own sake and make it right for your students. So pencil pushing is a very strange name. But really, what is the intuitive idea of an angle? Was it what I was doing today? I was twirling my thumbs 180 degrees. You did it half a turn. Literally, an angle is an amount of turning. For example, here's a pencil. Since I called this pencil pushing, there's a pencil. It's currently pointing that way. If I were to turn it, say, not half a turn, but say quarter of a turn, oh, it rolls, it'll be that way. That was literally quarter of a turn. Quarter turn. That's all an angle is intuitively. It's an amount of turning. A quarter of a turn is this. There it is, a quarter of a turn. Beautiful, quarter of a turn. Or if I wanted to say a third of a turn, I'm going to be really bad in my board technique here. I'll start this way this time. A third of a turn would be, third of the way around. Probably something like that, maybe. Is that a third of a turn? I'm guessing it's a third of a turn. There is a third of a turn. All an angle is an amount of turning. Great, 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 great. I know, I'm having fun. Half a turn. I should do half a turn. Half a turn, which would be, okay, start some direction. You know which direction you start. Half a turn would be, well, here, that's a full turn is all the way around. Well, half a turn would just be half of that. Beautiful. Half a turn would be that. Beautiful. Half a turn. Whoops, a funny arrow. That's the idea. If I drew a full turn, maybe I'll start pointing this way. Here's my pencil pushing. A full turn would be that. Bit hard to draw that angle, but you might draw something like this. Half a turn. Whoops, camera, focus, camera, focus. Bingo. So there's one turn. Actually, you can get kind of funky. Here's a picture of 3 turns. 3 turns. Loads of fun, loads of fun. The school curriculum, I'm going to tell you one thing. The school curriculum doesn't care whether you turn clockwise or counterclockwise. It doesn't care. Yet mathematicians care. Mathematicians make a difference between turning counterclockwise, they consider positive turning, and other directions, they consider negative turning, which is very weird. I can tell you a little story about that. So your kids will actually only not worry about angles in terms of which way you do the turning, but they will worry about later on the direction of turning. Because so much of mathematics was motivated by astronomy. So people noticed that the sun tends to rise in the east, and here's the east, tend to go up overhead in a great big arc and settle in the west sometime later. And people actually started drawing maps. For some reason, the convention was to put east to the right and north upwards and west to the left. There was actually Ptolemy, who actually drew a lot of his maps, a very famous Greek cartographer in about 200, 300 AD, somewhere around there. Drew a lot of his maps this way with east to the right. Why he chose east to the right, don't know, but they followed him. And that means, if you think about the motion of the sun, we always go from the right and we always head in this direction, which is really weird, because if you look at a clock, what way do things turn in a clock? Oops, sorry, let me draw a clock. 1, 3, no, that's 12. What am I doing? I can't even do clocks. 3, 6. Oh, how do you do 6? You do 6 like that. How do you do 9? Something like that. My point is, the hands of a clock turn this way, which is different from what happens in high school maths. High school maths always wants to turn the angles this way, yet the rest of the world turns angles clockwise. So let me tell you a story. I know why. I know why there's a difference. Think about the very first clocks people had. What's the simplest clock you can make? It's actually really fun to do this. It would be a stick in the ground. Just stick a stick in the ground. There's the ground and put a stick in it. And then what people actually did, they realized, the shadow moves. The shadow moves. And here's the thing. Stick a stick in the ground. As the sun moves around its arc, you'll see that shadow actually moves around the stick. People associated the direction of the shadow with clocks. And it goes this way. It goes this way, which is amazing. Now, warning. This is a major Northern Hemisphere bias. You guys in Victoria, on a sunny day, stick a stick in the ground and you'll see the shadow does not move clockwise. Because in the Southern Hemisphere, the sun hangs in the northern sky. Where I am in America right now, it hangs in the southern sky. For all Americans, the shadow goes this way. For Australians, the shadow goes this way. For people that live between the two tropics, the direction of the shadow changes from year to year. So this became a Northern Hemisphere bias to associate this direction of turning with clocks. Now, if Australians thought to make sundials first, everything would be consistent in math. We'd be drawing maps with angles going this way in maths and clocks going that way as well. So there is a human story about angles right off the bat. So an angle is an amount of turning. People associate the direction of turning with motion of time and clocks, but that's not really too much of an issue because people say, no, an angle is just literally amount of turning. So I can draw a picture, start here, turn like 1/6 of the way, and there could be 1/6 of a turn. Beautiful, Beautiful, beautiful. An angle is an amount of turning. Let's see. So since I'm just rambling today, this is the rambling experience in this little odd workshop, I need to point something out. At some point in America, it's in middle school, so it's beyond year 6. It's usually about year 7, year 8. People say an angle is 2 rays with a common vertex, which seems ridiculously dry and inhuman. And they say 2 rays, I guess it's a pointy thing, a ray is a pointy thing, with a common vertex. In America, they call this vertex. I wonder if they call it vertex in Australia. I don't know what the Australian curriculum does. The pointy bit, the corner is called a vertex. They say that's an angle. And I look at that and say, well, sure, but it depends, because maybe it was a pencil that turned that amount. So maybe this is the angle. Or it could be that a pencil actually started here and turned this amount. Actually, maybe that's the angle. Or maybe the pencil did something crazy, started here and went all the way around and all the way around and, oh, my video froze, and a bit more. That is, it started here, it's gonna be a messy picture, went all the way around, went all the way around, and then went a bit more. This is insane. So this is really confusing in geometry books in middle school and high school. Like, you just draw me 2 rays, what's the angle? Well, there's convention. The convention is assume it's the smallest amount of turning you can see, in which case it would be that amount of turning. And people don't worry about direction in school math. Either way, that amount of turning is the one you're talking about, unless you're told otherwise. They say, no, please make it the bigger of the 2 angles you see. Or please make it something absurd, spin around in place twice, and then turn the bigger angle. So if you're not told otherwise, it's always the smaller angle, which is how it is. Okay, great. I love this. I love this. Now, what was the title in this talk? The angles in a triangle add to 180 degrees. So I better start talking about triangles. So let's see, a triangle. It's a 3-sided shape. Whoop. Put it on screen. Hopefully you can see that. Great. Okay, how many angles do you see in a triangle? Why, I see 3. There's 1 angle there. There's another angle there. There's another angle there. And you learn, if you were to somehow get out a protractor and add these measures of these 3 angles up, it's meant to be adding up to 180 degrees. But my point is, that's hard. Protractors are hard. I don't even know what 180 means, really. All I know is that 180 means half a turn. I know what half a turn means. So actually, let me show you that these 3 angles really do add up to half a turn, literally, because an angle is an amount of turning. So here's a pencil. Here's a pencil. I am literally going to apply that amount of turning to it. And I'm going to add to the pencil that amount of turning. And I'm going to add to the pencil that amount of turning. And let's see what's happened to the pencil. Now, memorize how it's starting. My pencil's starting here and it's pointing this way. I'm going to literally apply those 3 amounts of turning to the pencil. Here goes. The first amount of turning. Zoom. Great. That pencil's now undergone that amount of turning. And I can see it's now pointing this direction. Oh, actually, here's something interesting. If I slide the pencil along the straight line, I'm not doing any turning to it. I'm just seeing where it's pointing. Okay, that's great. So they're still pointing the same direction. I've done no turning there. But now I'm in a position, I can now add this amount of turning. Well, that's marker, not something untoward. Marker to add this amount of turning to the pencil. Here it goes. I'm going to add this amount of turning. Here it goes. Zoom. Oh, so that marker has now undergone that amount of turning, and I've also added that amount of turning to the marker. Let's slide the pencil back. No turning, no turning, no turning. Straight line, no turning. Now let's apply this amount of turning to the marker. Zoom. Oh, that amount of turning on the marker, plus that amount of turning on the marker, plus that amount of turning on the marker. In fact, let me bring it back to the beginning. There's no turning, slide in the straight line. Look what's happened to the marker. That's the complete opposite of what it started with. It started off pointing this way, that's what my green arrow says, and applying this amount of turning, zoom, zoom, zoom. It turned half a turn. These 3 angles add up to half a turn, which people say is 180 degrees. Whoa, whoa. Okay, maybe that's very special about that triangle. What if I do like a really long, skinny triangle? Okay, in fact, imagine this is going 10 kilometers out that way. Let's make it a really long, skinny triangle. My question is, can you see in your mind's eye that these three amount of turnings must actually add up to half a turn as well? Can you see it in your mind's eye? But I'll start there for the fun. So I'm starting this way. Or you can start anywhere you like. Apply the first amount of turning. Zoom. Oh, kind of there already. Apply the next amount of turning. Zoom. Okay. Let me bring it over here. No turning, no turning, no turning. Straight line, no turning. Whoops, don't roll. Apply the next amount of turning. Zoom. Bring it back for comparison. That marker turned around, half a turn. Brilliant! The three angles of this triangle add to half a turn. In fact, I'm going to see if there really was 10 kilometers out that way, I could still actually see the same thing would happen in my mind's eye. This is crazy. All right, your turn. If the three angles of a triangle add to half a turn, what about the angles in a four-sided shape? Here's a strange, wonky, oh, I can say the word wonky, I'm in Australia, four-sided shape. What do these four angles add up to in a four-sided shape? Now, it'd be really cool if you had pencil and paper and a tiny little, like a tiny pencil. Do you have a paper clip or a hairpin or a bit of fluff or something you can turn in the corners? It's really kind of cool to actually do it. All right, I'm going to do it. I think I saw one person I think do it or do something else. So let's see what happens. Okay, I'm going to apply each of the four angles, four amounts of turning, because an angle is an amount of turning. Zoom. Oh, first of all, did you memorize which way the pencil is? Memorize that. Burn that into your brain. This has to be burnt into your brain. All right. Zoom. No turning. Zoom. No turning. Zoom. No turning. Zoom. No turning. Ooh. Hang on, what was that? What was that? Okay, I'll show you. I'm gonna do it again. Do it again. All right, pencil starts this way. Now turning one. Zoom. Sound effects are very good. Slide, 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 slide. Mounted turning two. Zoom. Okay. Slide, 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 slide. Mounted turning three. Oops, camera focus, 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 focus. Don't need the funny focus things going on. Mounted turning number three. Zoom. Has it focused? Now it's focusing. Good. All right. Slide, 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 slide. Mounted turning four. Zoom. Slide, 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 slide. Well, look at that. One full turn. Okay. I've got a question for you. That was a very, come on camera, that was a very nice four-sided shape. What if I did a non-nice four-sided shape? Here's an un-nice one. One edge, second edge, third edge, fourth edge. It's like the Star Trek symbol. It's got four angles. And I think we need to talk about, be very clear that every time we were doing the inside angles, and I think it's going to be an issue for us now because we have to be very clear. What do I mean by the inside angles? Well, there's an inside angle. There's an inside angle. There's another obvious inside angle. And then I worry about this corner. If you think about it, the inside is all this stuff. This big one must be the inside angle. So do those four angles also add up to one full turn? I mean, they did for this quadrilateral, one full turn. Are these also one full turn? Try it out. I'll pause. I'll drink my water while you're doing it. So draw yourself a funny Star Trek type symbol. Make sure you're clear on which the four interior angles are, the four amounts of turning, and apply it, some object to each of those four amounts of turning. is it, again, one full turn? All right, so my co-hosts, are people saying in the chat, is it one full turn or not? Are people saying things?
James, we have someone saying their mind is blown.
Okay, from a little pencil. I love it, a little tiny pencil.
I think we think it's one full turn, don't we?
Yeah.
Yes. There's a bit
Okay. All right, my turn then, Chloe. Oh,
yes,
where's a good starting spot?
Turn.
One full. Everyone's saying one full turn. Okay, so start this way. I'll make it very clear. Zoom. Slide. Zoom. Slide. Oop. Or now on the inside. Zoom. Slide. Zoom. Slide. Beautiful. There it is. Looks like that pencil went through one full turn. All right. Okay, one full turn. Okay, would you like me to be nice or not nice next? Oh, someone type in nice or not nice in the chat. Whoever types in the first answer, I will follow.
James, we are saying not nice.
Okay, you got it.
We are here for a challenge in Victoria. We're
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a 10-sided shape. I want to know how many turns do the inside angles of a 10-sided shape, draw your own 10-sided shape, make it weird and wild like mine. What do the 10 angles inside a 10-sided shape you asked for not nice, there it is, not nice, add up to? Good luck. I can probably go away and make myself a latte or something, and by the time I come back, we might still be struggling. If you think of the answers, just type into chat. I bet we're all going to be all over the place. This one is actually very nasty. So we're all friends. We can share each other's first attempts. I'm curious what sort of answers people are getting.
James, we have 4 full turns, 880 degrees. And then we have comes back to the same direction for me. I'm working on that number, which I think is terribly boring.
And I think it might be 3 turns.
3 full turns, 4 full turns, 880 degrees, and just comes back to how it started. Okay, I'm with you. Clearly it's my turn. All right. Oh gosh. Okay, so we have to be really careful. So I'm going to start here. I don't know why I just chose that one at random. I'm going to need help. I'm starting off pointing this way. All right, let's be really careful. Angle number 1, zoom. Angle number 2. Oh, I'm not quite one full turn because I see it's not quite aligned yet. Here comes angle number 3, but look at this. If I stop there, I've just realigned So I've actually just undergone one full turn already. I'll do ding, ding, ding. That's one full turn, but I've got to keep going beyond one full turn. Beyond one full turn, I'm still going. All right. Zip. Oh, ding, 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 ding. Just right there is a second full turn, but I keep going a tiny bit more. Zip. Okay. I apply this amount of turning. Zip. Apply this amount of turning. Zip. Apply this amount of turning. Zip, 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 zip. Oh, ding, 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 ding. Back to alignment. That's a third full turn, but I keep going beyond 3 turns. Doing a lot of turning here. Zip. Yep. And zip. And finally the last one. Ding, 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 ding. Fourth full turn and back to where I was. Beautiful. 4 full turns. There it was. And it was also started back to where we were. Both answers were correct. I love it. 4 full turns, 880 degrees. How many degrees is that? That's too hard for me. That's arithmetic. That's really tough. I can't do arithmetic. Some number of degrees. Actually, we should talk about degrees. There's a really interesting human story there. But I love this idea because actually, before I get to the human story of degrees, we were saying this. This was half a turn. Oops, come on. The angles of a triangle after half a turn. And then we did something crazy like this and saw one full turn. But some student might notice, excuse me, James, if I just chop this figure in half, I see a triangle there. That's half a turn of angles. That triangle is half a turn of angles. So I got 2 triangles. I got 2 half turns. 2 halves is 1 full turn. Which then makes me figure out this crazy 10-sided shape. Can I chop that into triangles? Oh, there's half a turn there of angles. Well, that's not a triangle yet. Oh, but that's a triangle. There's half a turn of angles there. Half a turn of angles there. Half a turn of angles there. More triangles? Sure. Half a turn of angles there. More triangles? Sure. Half a turn of angles there. Half a turn. Half a turn. Oh, all the angles made up to a half plus a half. Half plus a half. Half plus a half. Half plus a half. 4 full turns. That's a big epiphany after a while to realize that actually if you chop the shape into triangles, you can avoid some hard work. But that's an epiphany to have at some point in your career because it's actually much more fun just to turn the angles around, have great big debates. Is it 4 turns? Is it 3 turns? Is it 5 turns? Is it 7 turns? Lots of fun. Oh, a question or something? No. All right. So then, okay, since we've got another 14 minutes and 1 second left together in our lives, someone mentioned degrees. Degrees are weird. Degrees are weird. Because we like to say, if I were to walk 1 full turn, so here's me, walking all the way around, I've walked 360 degrees. That is really strange. Who chose the number 360 for the count of degrees in 1 full turn? We say 1 full turn equals 360 degrees. Now, this seems like a strange question to you because we are so used to the number 360, we don't even question it. But someone had to say, let's choose 360 for the number of degrees in a circle. Someone must have first came up with that number. For example, if I said to Ellen, pick a number for the number of degrees in a circle, and she just pulls out 360 out of the air, we say, okay, but that's weird. Why 360? So my question to you right now, just for your own personal adult selves, and maybe for your students too, why do we humans choose the number 360 for the number of degrees in a circle? It's just a weird number out of the blue. Does anyone have any thoughts where that number 360 comes from? I'm curious what people might be saying in the chat. Where did that number 360 come from?
Nothing in the chat box just yet, but I'm sure people are thinking.
You're thinking, and plus we have that delay, so we have a delay. So I should be chatting away. I should be saying.
There are some other interesting comments saying, "I love you, James." Oh, and,
I love you back.
Shannon has said, "Does it come from the Babylonians?"
It does come from the Babylonians. And okay, I will tell you, Babylonians are very clever mathematicians. They, like me, they do not like hard work. They will work very hard to avoid hard work. So actually it does come from the Sumerians and the Babylonians about 4,000 years ago. So let's ask this question. The point is, this is a very human story. Why did we humans choose the number 360 for the number of degrees in a year, degrees in a circle? And you think about it, we humans are stuck on this planet, and what's one very natural cycle we humans experience? It's the number of days in a year, Okay, so we humans are very aware of the seasons of the cycles we go through. So we think of that the year is a very natural cycle. So we often associate the number of days in the year with one full cycle. Now, let's be very human. How many days are in a year? Now, those Babylonians were very clever astronomers. I bet most people are saying 365 days in a year, except for maybe leap years, but actually those Babylonians were very aware it's 365¼ days in a year. And that's why over leap year, because every 4 years we have to make up that quarter we missed before. So actually, we should be saying one full cycle for us humans should be 365¼ degrees. Now, let's be human. Would you like to do maths with the number 365¼ all the time? No way, it's horrible. It's a horrible number. So what's the very natural human thing to do to that number? Let's be very human. The natural human thing to do is to round it, Now, suppose I said to you, out of the blue, let's think this through really carefully. Okay, Max, I don't know if there's a Max in the audience, but I'm gonna pretend there's someone called Max in the audience. Max, if you had to round this number, 365², what would you round it to? And Max could say, I think two very natural things. If you round it to the nearest integer, you just round to 365. That would be the natural thing to round to. Or you might say, let's round to the nearest 10. Think about it. What's the nearest 10? It's actually up to 370. We're just over the halfway point. So up to 370 is the nearest 10. Yet those Babylonians said, no. Let's do the counterintuitive thing. Let's round down to the nearest 10 to 360. And they chose that one over all three choices, which is weird. Why? Why did they choose 360 over something that seems more natural? If I said to round the number, either round to the nearest 5 or the nearest integer, or round to the nearest 10, they went down to 360. You think about this for a while. They're humans. They don't like doing hard work. So if you're often working with geometry or for them astronomy, you say, okay, I'm often dividing things into halves and quarters and fractions and stuff. The number 365 is not even friendly for dividing to half. Let's not do that. You can't even do halves nicely. So let's get rid of that one. We can do 370 and a half. That's fine. We can do 360 and a half. That's okay as well. But you might want to do thirds. 360 is divisible by 3. 370 isn't. 360 is divisible by 4. If you want to do quarters, 360 is nice. 370 is not divisible by 4. 360 is divisible by 5. I guess that was divisible by 5. 360 is also divisible by 6. It's not divisible by 7. Actually, neither is 370. In fact, nothing's ever divisible by 7. But 360 is also divisible by 8 and 9 and 10 and 12 and 15 and 18 and 20 and 24 and 30 and 36. It is ridiculously divisible. So if you're a Babylonian doing nothing but maths and bits of sand in your head, 360 is a much better number for arithmetic. And we humans said, look, let's go with the number 360, the number of degrees in a full cycle. So instead of doing 365¼ which is what it should be for us on Earth, we rounded to a much nicer number to make our maths easier because we don't like hard work. So one full turn is 360 degrees. One full turn is 360 degrees. And so half a turn, the number of degrees in a triangle, will be half of that, 180 degrees. And we did a 10-sided shape that's 4 full turns, would be 4 times 360. 720, 1,440 degrees. So that 10-sided shape had that many degrees. Okay, just to be fun, here's my question for you in the remaining 8 minutes and 1 second. How many degrees are in a Martian circle? And you've got terrible handwriting here. I don't know why you hired me to give workshops for you. You can't read my handwriting. How many degrees are in a Martian circle?
So we need to
I think
know.
that's a really strange question, but actually, it's a legitimate question. They wouldn't say 360. They wouldn't go through the process we went through. They would say, well, there's 365¼ days in an Earth year, therefore, let's round to a nicer number, 360. What would Martians do? What do you need to know? And you realize, oh, well, Martians might go through the same sort of reasoning that we did, say, okay, how many weeks, we're living on this planet that goes around the sun, but you need to know how many days are in a Martian year. Okay, Google, how many days are in a Martian year? Can someone quickly Google it? We live in the 21st century. We've got Google at our disposal. or Ask Siri, or one of the equivalents Alexa is in Australia. I don't actually. I've got all these things are American in my head. Do you have Siri in Australia? Do you have Alexa in Australia? Do you have Google in Australia?
We have all of those things.
But all those things. Okay, I've been in America too long.
Can you Google it?
Yeah, how many days in a Martian year? That's what Martians would do. They'd ask how many days. They'd figure out how many days are in their year.
Just waiting for.
Oh my gosh.
Maybe Peter was going to put something in about that. He was talking about Martians. Oh, we have 687 days, says Jessica and Rachel.
Okay. Any other answers?
Not as yet. We've got multiple 687s.
Yes,
667 is another answer.
I found 687.
Okay. Warning. There's danger here. The question is, did your Google answer how many Earth days are in a Martian year, or did it answer how many Martian days are in a Martian year? Because I happen to be married to a NASA scientist. I actually know the people that work on the Mars rovers. They tell me one Martian day is slightly longer than an Earth day. It's 24 hours and 37 minutes long. That's how long a Martian day is. And in fact, the word for a Martian day is soul. Have you heard the word soul? Have you seen the movie The Martian? Have you read the book The Martian? It's all about souls. So this is the number of Earth days in a Martian year. That's Earth days. That's irrelevant to Martians. They don't care about Earth. This is actually the number of souls. This is the number of Martian days in a Martian year. This is what Martians count. Martians would count 667 souls in their year. Whoa. By the way, let me tell you a side story, since I am married to an actual NASA scientist. So those people that work on the rovers and Perseverance and all the rest, they operate by solar power. So they can only operate during Martian sunlight. So JPL, Jet Propulsion Labs, the people that run the Martian solars, the rovers, had to actually make all their staff come in during Martian sunlight hours. That is, they made special watches that didn't run on 24 hours. They actually ran on 24 hours and 37 minutes. So you had to arrive at work at 7 o'clock in the morning according to your watch, whatever it was, irrespective of the rest of the day. So they were arriving to work 37 minutes later each day so they could be at sunrise for Martian sunrise. It apparently drove them batty. That UCLA, University of California, Los Angeles, started doing a sleep study on these people. How can you disrupt your work hours by 37 minutes every day? It was really untenable. So they gave up on that. So they don't longer have those watches. But I'd love to have one of those watches they did make for those people. That'd be so cool. Anyhow, so the 667 souls in a Martian year. So the question is, how many degrees in a Martian circle? What do you think Martians would say? And now it's speculative, because obviously they probably don't want to work with the number 667. They probably want to round it to something nicer. I don't know what Martians would round it to. What are people saying in chat? What might they round it to?
We have... Are you on? Sorry. All right, we've got, oh my gosh, Trevor.
Trevor's writing you a novel.
What is that?
Paul Circadian rhythms he's talking about. Cassandra's guessed 640.
I like 640 as well, Kat.
Yeah, it's 640, maybe 660. They probably do the same thing. They probably don't like hard work. They'll choose a number that's divisible by 2, by 3. Probably that's divisible by 3, by 4, by 5, by 6, maybe by 7, probably not, by 8, maybe, who knows. You're right, they do the same sort of thing. My only point is the entire maths curriculum is about humans, about human stories. The number of degrees in a circle is literally a human story. The human year is why we chose the number 360. Let's not deny our fabulous students the humanness of mathematics in our curriculum. Let's share the human stories. And let's just share the human play. I mean, it's so fun to just turn a little pencil around. You've got to love it, that you can actually see, get the intuitive feel. You know, when you get to high school maths gets so dry and tedious after a while that we say an angle is a vertex, is two rays meeting at a vertex. Doesn't mean anything. The actual intuition is the amount of turning. And it's so much easier to speak in full terms. That's one full turn. Oh, I guess I better translate that to degrees, 360 degrees. Degrees are actually unintuitive. It'd be so much nicer if we talk about half a turn or a third of a turn or a quarter of a turn like we do in everyday life. Anyhow, that's my only point, is that maths can be a beautiful, organic, playful experience without letting go of the rigor and the real learning. We can develop the intuition, and we can be extraordinarily joyful and human about it all the way through. It is chock full of humanness. because maths was made by humans for humans to be enjoyed by humans. So let's make it human for our kiddos too. So on that note, I'm going to stop sharing my screen. We've got about 59 seconds left. Oh, 47 seconds left for questions. Ask a lot of them quick and I'll answer them quickly. 47 seconds.
Excellent. So,
questions?
James, we will monitor the question box, and Ellen, I actually have one question for you.
Yes.
Why does the ball have to be red?
It just does. What can I say? It just does.
I'm assuming this is coming down to your amazing visualization and making it realistic, which is great.
Oh, there we go. There we go. Thank you. Well, my pleasure. Well, that's what maths is. Maths is a very visual pursuit. It's just, you know, that's how it is. Let it be joyful, visual, and intuitive and real.
Absolutely. And another question from me was, is it important to make the sound effects?
Yes. Okay. Did you have fun? Did you have fun with the sound effects? Are they sticking in your brain? Yes, they absolutely are. They stick in your brain, and let kids choose the sound effects. Oh, we need a sound effect. Zoom for that, or should sliding have a sound effect? And just it makes it. You know what?
So we'll have to close it off then. We
Okay.
do have one more question: is when are you coming back to Australia?
Good luck.
When I'm invited. And there's no quarantine. I don't want to do 14 days of quarantine, 2 days of visit, and 14 days of quarantine coming back. That's a bit too much commitment on my end. I'm sorry.
We absolutely, Ellen and I both had we had many epiphanies. If you could see us, we were hitting each other, and lucky we're on mute, there may have been a few curse words. But thank you so much for sharing the human stories and the nice numbers with us. A reminder to everyone, we will be back at 11:20, where Alex Box will be speaking to us. And please don't forget to check out the virtual delegate satchel and touch base with our sponsors and exhibitors. So we'll see you all in about 8 minutes. Thank you.